Assalamualaikum, Bismillahirrahmanirrahim. Today we will start our chapter number 5. This is from your book Normal as Nice. The name of the chapter is the reduction of the multiple subsystem, and there are multiple techniques for the reduction of multiple system. In today's lecture, we will cover the block diagram reduction, or how can we reduce a system by using a block diagram. Actually, as for we worked with individual subsystem represented by a block with an inputs and the outputs. When there are more complicated system, they are represented by interconnection of subsystem. We want multiple system as a single transfer function. Actually, in this chapter, multiple subsystems are represented in two ways. One is the block diagram technique, and another is the signal flow graph. Although neither representation is limited to particular analysis and design technique, usually block diagram is used for frequency domain, and the signal flow graph is used for state space analysis. Both techniques has advantage or disadvantage. The signal flow graph have an advantage over block diagram that they can be drawn more quickly, they are more compact, and they emphasize the state space. Similarly, block diagram algebra will be used to reduce block diagrams, and we use Mason rule to reduce signal flow graph. Okay, for today's lecture, in today's lecture we will study how to reduce multiple subsystems block diagram into a single transfer function. We will start from this slide. Before starting the block diagram technology, we should be familiar about these terms. This is the simple block diagram. We should know that R of S is always used for the input. G of S is forward gain of this block diagram, and if the arrow is coming from forward path and ending at the forward path summing junction, that will be the feed forward path. And this is the circle with the cross sign, this is called the summing junction. C of S is our output of the system, and if there is any branch entering or leaving in forward path without any summing junction, that will be the pick off point. This is our pick off point. This is pick off point, and this is the pick off point. These both are the pick off point, and these two are the summing junctions. And this feedback path, as you are already familiar, feedback path, feedback is coming from our output of any subsystem or system, and it is fed back to the input to check either the output is a desired output or not. So this is the feedback path, and H of S is always used for the feedback gain. You should familiar about these terminologies before starting the block diagram reduction or technique. Okay, this is the simplified simple block diagram in which there is shown one system. The transfer function of the system is G of S, and the input is R of S, and output is C of S. The simplified block diagram relates input of the system to the output of the system through a through a forward gain block. Okay, and here is the summing junction. Here are three inputs. One is R of S, other is the R2 of S, and the third one is the R3 of S. And we should know what are their effect on is summing junction. Either they are summing or they will be subtracted after this summing junction. These signs show their the response, show either this input will be subtracted or added or at the output. This is the R1 of S, this is our input, this is our second input, and R3 is the third input. And what will be the C of S in this case? As it's gone through, all three inputs are gone through the summing junction, then the output will be the R1 of S plus R2 of S, and R3 subtracted from the both inputs, and C of S will be the R1 of S plus R2 of S minus R3 of S. This is the summing junction. Okay, what happened if we have multiple subsystems? As shown in this block diagram, we have three subsystems. The transfer function of first subsystem is G1 of S, and the second is the G2 of S, and the third one is the G3 of S. Actually, the purpose of block diagram reduction technique is to reduce the multiple subsystems into a single block diagram. So we are first but we should understand the basic rules of reduction of this block diagram. So if three subsystems are in series or in cascaded form, what will be the output? How can we replace these three block diagrams into a single block? So this is the R1 of S is our input, G1 of S is the transfer function of this subsystem. This can be any electrical, mechanical, translational mechanical, or any subsystem. We are considering that the transfer function of this function, this subsystem is G1 of S. And what would be the output after the first subsystem? First, after passing the input from the first subsystem, this will be the G1 of S multiplied by R of S. Means that the input will be multiplied with the transfer function of the first block, and after second subsystem, the x1 of S will be the input of this block multiplied by the transfer function of this subsystem, that is G2 of S multiplied by x2 of S, or we can replace x2 of S with G1 of S and R of S. Similarly, what will be the C of S? C of S, as you know, C of S is our output. C of S will be equal to the input of the G3 of S, the third subsystem, and the transfer function of that subsystem. So C of S will become G3 of S, G2 of S, G1 of S, and R of S. And we can replace this whole subsystem consist of three subsystems. We can replace these three subsystem by a single block diagram, single system which have the single having the transfer function G1 of S, G2 of S, and G3 of S, having input R of S and output R of S. The function of this the output of this system will be the same as as the output of the above system. So this is the benefit of the block diagram technique, that we can reduce a multiple block system or complicated system into a single block or single transfer function, and we will get the same output. Okay, now what happened if we have these blocks in a parallel? What will be the output? What and how can we reduce the parallel blocks into a single transfer function? Here we have R of S as our input, and the three subsystems G1, G2, and G3, or the transfer function of these are the transfer function of these three systems are in parallel. What happened? Basically this is the pick off point, as we have already studied that this is pick off point, this is the summing junction. The output of the first subsystem will be the by using the same concept, the output of G1 of S will be the x1 of S will be, what will be the output? R of S multiplied by G1 of S. Similarly, we can write the output of these two systems as well, G2 of S and G3 of S. So x1 we will get x1 of S, x2 of S, and x3 of S, and these are the output of three subsystem. And what will be the C of S? C of S, as there is a summing junction, and these output will be either added or subtracted. So we can write C of S will be equal to the G1 of S. We have taken R of S as common. We have taken R of S as common, as R of S is multiplied by the transfer function of each subsystem. So we have taken R of S as a common, and rest will be with plus minus G1 of S, plus minus G2 of S, and plus minus G3 of S. So we can represent this parallel block diagram by a single block, and the input of this will be the R of S, and output will be the C of S, and here is the transfer function of this block. Okay, actually there are three possibilities in any complicated system, that either the subsystems will be in series, or the subsystems will be in parallel, or the subsystems will be in the form of feedback bar. So we have we have learned how to reduce series and parallel Sorry, the recording was stopped unfortunately in the last lecture, so we'll continue the lecture from where we will discontinue our lecture. We were studying how to reduce a block diagram. So we studied that there are three possibilities in any complicated system, that either the subsystem will be in series or parallel or in feedback block. So we have studied in the last recording that how to reduce a series and parallel subsystem. Now we will check if there is an option that we have subsystem and which have the feedback block. So here is the input, and here is the actuating signal or error signal. As you know, the actuating signal or error signal is the difference between the output and the input. The error signal will be equal to the R of S, our input, and that will be added or subtracted depend upon either the feedback is the positive feedback or the negative feedback. So the input will be added or subtracted with the this feedback. And what will be this feedback? H of S, it will become the output multiplied by the feedback block H of S. So errors will be the R of S or input plus minus output into the feedback block, the transfer function. And what will be the C of S? Means the output will be the G of S, this plant or controller, and multiplied by the input of the plant. And what is the input of the plant? Input of the plant is E of S, and we have already find what is the E of S. We will put the value of error signal in this, and by putting the value of error signal in this equation, we get C of S will be equal to G into R plus minus C of S into H of S, and we will simply solve this equation, and we will move the terms of C of S on the left hand side of the equation and rest term on the right hand side of the equation, and we will get the transfer function, that is the transfer function is between the output and the input of the signal, means C of S over R of S, that will be the equal to G of S over 1 plus minus G of S into H of S. So we have studied how can we reduce a complicated signal by using a block diagram technique. And I will repeat again that there are three possibilities. One is either the subsystems are in series or cascaded form, other is either these are in parallel blocks, or third one is either they are in feedback block. So now the next method we will study that what will we do if our block diagram is not as per required, means either they are not in the form of feedback or series or parallel. Then we will move our summing junction or our transfer function before the summing junction or after summing junction. So what will be the effect of moving any our summing junction before or after any subsystem? So if we move, this is the case one, if we move our summing block to the right, means summing junction is here, and what is the purpose of moving this summing junction after or right on the subsystem? Basically the purpose of moving is just to maintain our system in standard form. It means if there is any complicated system and we want to write the transfer function of their system, and to write a transfer function, the system can be simplified. Either it will be in series, parallel, or in feedback path. If the feedback path is not appearing in that, then we can move summing junction from right or left on the summing junction to get the standard form, and so that we can write the transfer function of our system. So if we move our summing junction to the right of the subsystem, what will we do? We will multiply all other branches with the g of s, because this g of s is multiplied by all the terms uh, me, coming from all the inputs coming from this summing junction, because in this case what will be the input of g of s? That will be the equal to the r of s plus minus x of s, and this input will be multiplied with this g of s. So if we move transfer function, or sorry, we will move some summing junction after the that block, then it will come with the input, and it will be not multiplying with the x of s. So we will add g of s with the other branches as well. And the second case, if we are moving this summing junction to the left of the block, means summing junction here, the summing junction is we move summing junction from this point to the left of the transfer function. What will happen actually in this case? This g of s is already multiplying by with r of s, not with x of s. If we move this g of s after the summing junction, that it will be multiplying with the both, so our output will be changed. So to avoid this, we will multiply x of s with 1 over g of s, so these both will be cancel out each other, and the input from this x of s will remain x of s, not x of s into g of s. So you should remember this point. If we move summing junction to the right side, we will multiply all other branches with g of s, and if we move on the left side, we will divide we will multiply all other branches with 1 over g of s. Okay, now the third option is moving block to the left of the pick off point, means we have this block and we move this on the left of the pick off point. So what happened, as it is very clear from this block diagram, the output at this g of s will be the input into g of s, and here is no g of s is multiplied with this is the we are getting input, and same we are getting at the output. And in this branch as well, there is no subsystem, or you can say it has unity gain transfer function. We are getting r of s, and we are getting same r of s at this output. So what will happen in this case, if we move this pick off point to the left of the pick off point, so we will multiply other two branches with 1 over g of s, so the effect will be cancelled out, this g of s will be cancelled with this, and the output will remain the same. Now the last case is this, that if we move block to the right of the pick off point, means here is the g of s, and we move we want to move this pick off this block to the right of the pick off point. What will happen? Actually this g of s is multiplied with all these three branches, so it's so simple. We will multiply, we will add g of s in all these three branches, and the output of these three branches will remain the same. So students, now you are very familiar about block rotation techniques rule. I will repeat again that for block rotation we should familiar about the terms: what is pick off point, what is summing junction, what is feedback path, what is forward path gain, what is the input, what is the output. After knowing this, we should familiar about the terms. What is block what is the summing junction, and if we move if we want to reduce series block diagram or parallel branches or feedback path into a single transfer function, what will we do? And we should also know what will be the effect of moving any block or summing junction before or after pick off point or any summing junction. So here is the example, simplify the block diagram. Now we have to simplify this block diagram into a single transfer function, and it's very simple. As you know, you can see that these summing junction are in series, and there is no subsystem between these summing junction. So we can replace these three summing junction by single summing junction. And remember, we will not change the sign of this feedback has, this is negative feedback, this is positive feedback, and this is again the negative feedback. Now these three feedback loops will combine on a single summing junction, and as you can see, these are in parallel. H1, H2 and H3 are in parallel. We can replace these three by a single block diagram, as H1s is negative, H2 is positive, and H3 is negative. So we can write H1 of S minus H2 of S plus H3 of S, and we will put a minus sign here because it will become minus H1 of S plus H2S of S minus H3 of S, as shown here. Now what will the next step? Next step will be that G2 and G3 are in series, so we can replace these two blocks by a single block. Now you can see that a form is appearing that in which we can reduce this block diagram by a single transfer function. As you can see that this G2 of S, G3 of S, and this are appearing in a feedback path, and in feedback path what will be the output of system? That is G of S, this is G of S over 1, either plus or minus depend upon the sides, plus plus minus into G of S into H of S. So this is simple. We write the equation. This is the G of S, this one is 1 plus G of S into H of S. So we have written this, and this G1 of S will multiply with this function, as after this feedback, the feedback and this one will be in series in cascaded form. So the transfer function will become G3 G2 into G1 by 1 plus G3 and G2 by this. So we have replaced this complex block diagram into this simple block diagram, in which we have a single block which have one input R of S and one output C of S, one input R of S, output C of S, and the transfer function of the system. So this is the benefit of using the technique block diagram, in which we reduce a block a complicated circuit into a single block. So the output of this system will be the same as the output of this complicated circuit. So I hope the rules are very clear to you. For your practice, you have to simplify this block diagram. You can practice this at home. This is also very simple block diagram. You have to use the same rules as we have done in the last example. I am giving you some simple guidelines. As you can see that this S and this S, these two are in series cascaded form. You can replace this by S into this, means as this will be replaced by a single S square. In the next step, what will you do? You will add this S square with this 1 over S, as and in the next step you will multiply, as this is a summing junction. You will move this pickoff point, and after this then you will solve these blocks. You will get a transfer function, and the transfer function will be in the feedback with this S, and at the last step you will apply the feedback path transfer function, which is G of S. G of S is the transfer forward gain transfer function by 1 plus or minus depend upon this sign into G of S, means forward path transfer function into this feedback path transfer function. So you will get the result, and you will simplify this block diagram. Okay, you have other lot of examples on your book. You can solve these examples and practice problem as well, and in the end of this chapter, or you can also solve the skill assessment for your practice. In the next lecture we will inshallah solve further examples, one or two examples of this block diagram detection, so the concepts are more clear to you. Okay, see you in the next lecture. Thank you. Allah Hafiz.